We are going to talk about the assumptions of the ideal gas. So there are two sets of assumptions. The basic assumption is not what you must memorize, because that is what you have learned in your secondary school, right? Or high school. So what we are going to look at is the simplifying assumptions here. So there are altogether 6 simplifying assumptions. And when they ask you for the assumptions of an ideal gas, you have to state these assumptions, all right? So these simplifying assumptions are the one that you must state, okay? Now, I'm going to go through with you what it means. In the exam, you just have to write this down. If they ask you for 3 marks, then you write the first 3. 2 marks, then you write the first 2. It's up to you. Right, so now let's look at the assumptions here. The first one, the intermolecular forces are negligible. So this one, I think you have understood from the previous chapter, right? Temperature. Okay, that what kind of intermolecular forces usually exist between the molecules? Brandon, what type of forces? Attractive or repulsive, or both? Actually, it's both, but generally attractive, yes. So most of the time it's attractive. Well done, Brandon. Alright, so at least you remember. Alright, so generally they're attractive because at the equilibrium separation where there are no forces, anything closer is repulsive, anything further away is attractive, and most of the time they're attractive. Alright, and so these are the forces between real gases, but in ideal gases we assume that these are negligible. Alright, the second one, the volume of the molecules is a negligibly small fraction of the volume occupied by the gas. So what it means is that if you guys are in this room, we're all atoms or molecules, right? If I were to add up your individual volumes, total them up together, that is what they mean by the volume of molecules. But if I were to compare this total volume of all your bodies to the volume of this room, that is the volume occupied by the gas. And your total volume will be negligible if I consider the volume of the room. Do you understand what I'm trying to say? Okay, so that is important to us because then it eliminates the need to consider whether you're talking about large gas molecules, like for example neon or oxygen, or small gas molecules like hydrogen. It doesn't matter because you total up the individual volume of atoms, it will still be negligible compared to the volume of the room. Do you understand that? Volume of the gas. Right, third one is random motion. So what does a random motion mean, Kun Yu?
Particles move randomly.
Randomly what? What does it mean by random motion? Simply move. Randomly means what? Joseph? Or in other words, they move in every possible direction. But no particular direction means not moving. They move in every possible direction, number one. Number two, they also move with different speeds. Understand? Now that is very important. You know why? Let me tell you why. Now, so imagine if you guys were atoms or molecules, and you all are free to move in every direction. And assuming you could float as well, so you can, because imagine there's no gravity, you can move anywhere you want. So some people will be moving diagonally, whatever, and you'll be moving in 3 dimensions, right? Because this room has length, width, and depth. So let's say you move in 3 dimensions, then I can resolve your velocity to 3 components, which is x, y, z. Am I right? So if everybody's velocity can be resolved to 3 components, which is x, y, z, so you will get like vx, vy, and vz. So if I were to total up everybody's horizontal component and divide by number of molecules to find the average, and I add up everybody's vertical component and find the average, and I find the total of the z components, and I find the average, will they be the same? Do you agree it must be the same? Because it's random. So every direction have equal chance of getting the same value, right? Am I right? So therefore your average of your horizontal average of your vertical, average of your z component velocities, all must be the same. That's what it means by random. Okay, so you don't have like average in one particular direction higher than the other. Okay, so that is what we mean by random motion. Fourth one, the collisions with each other and the wall are elastic. Actually, it should be walls, should be elastic. So why must it be elastic? What is the significance of elastic collision? You see, when they are, how do you know they are elastic collision? Okay, let me just ask you, what's the meaning of elastic collision? Grace? What is the difference between elastic and inelastic? Elastic is can bounce back, and inelastic? No, inelastic also can bounce back. Perfectly inelastic only cannot. Kimberly? Elastic was what? Kinetic energy conserved. Okay, so it is important to understand that the kinetic energy is conserved. But why must it be? How do you know it's conserved? How do you know the collisions are elastic? Can you see the gas molecules colliding with each other? Can you see them colliding with the wall? Cannot, right? So why do you say then they are elastic? So the evidence is the pressure is constant. Pressure of the gas is constant. Example, you blow a balloon, you tie it up tight, it will maintain its shape for a very long time, right? And it will actually shrink due to leakage, but that all takes a very long time. But if you look at the gas, right, if it continually collides with the walls of the balloon, if it loses Ke, wouldn't it slow down? And if it slows down, wouldn't the pressure drop? And then your balloon will start to shrink immediately. Does that happen? No, right? So therefore, we maintain that the collisions must be elastic. So every time it hits the walls of the balloon and also collides with each other, there's no loss in Ke. That's why they can always exert the same force and therefore the same pressure. Understand? Okay, right, next one. What about this fifth one, uniform velocity? Now, what you're trying to say is this. In between collisions, the molecules will be moving with uniform velocity. In other words, if let's say you consider one atom or molecule hitting, let's say, one wall, after hitting the wall, it bounces back with the same speed because it's elastic collision. Then as it is moving, if it doesn't hit with any other molecules or it doesn't hit with any other walls, then its velocity must be constant. Why? Because there are no intermolecular forces. If there were intermolecular forces, as it passes by a nearby atom or molecule, then you get attracted, right now. Then you will deviate. But it doesn't happen because there's no intermolecular forces. Okay? Very important now. So in between collisions, they're moving with uniform velocity. That means speed also constant, direction also constant. And the last one, which is also very important. Now, normally in your topic of dynamics in your AS, when we talk about force is the rate of change of momentum, this is what we will do. Let's say you have one atom or molecule hits this wall here, okay, one of the wall here. So to find the force exerted on the molecule, we will find the rate of change of momentum. That means you'll find the initial momentum of the molecule, the final momentum of the molecule. You will subtract that. So let's say going in is mu. After bouncing, what is the momentum? Because it's elastic collision, what will be the momentum? Ashley? Mu, but wouldn't it be in the opposite direction? So what's the momentum? Negative mu. So going in is mu, coming back is negative mu. What is the change in momentum? Esther? No, going is mu, coming back is negative mu. So mu minus negative mu gives you 2 mu. So your change momentum will be 2 mu. But you know what time we will usually take? We will take the impact time, right? That means the time that the molecule is in contact with the wall. But for ideal gas, because the time here is too short, that means the time that the molecule is in contact with the wall is too short, we don't take that time. What we take is the time between collisions. That means after colliding with this wall here, how long it goes to the opposite side and come back again to the same wall. We take that time. Understand that? So we will take 2 mu, but we will take the time it takes to go away from this wall to the opposite end and come back again. Okay, so that is something very unusual. Alright, that gives you the force. So these are your assumptions of the ideal gases. Now why they call it a simplifying, why they call it simplifying assumptions? Because with these assumptions, it will simplify our derivation of our next two formulas. So our next two formulas, right, will be using these assumptions as well. Hope you understand. Alright, so that's it.